Hi folks, it's Glenn again with the practice exam, just continuing with number 7 here, the electron configuration for Sn, which is tin. Sn is located here. You are getting a periodic table, and here is tin, Sn. So, whoops, I don't want to see this. All right, so Sn is right here. How do I find the electron configuration? Well, I'm going to use these numbers. These are just the numbers of the rows. If these numbers do not appear on your periodic table, you can just jot them down on a piece of scratch paper. So the first row is 1, the second row is 2, the third row is, it goes like that. All right. You'll also need to know the orbital names, and they are given by the blocks. This yellow block here, including the green, this is the S block, S as in spectral. This pink block down here, just this pink rectangular block. It does not extend this way, but just this pink rectangular block here. This is known as the D block, D as in diffuse. And this block over here, this green block including all this other stuff connected to it in almost a rectangle, but with this helium sticking out, this is all known as the P block. And down here, these two rows of elements, this is known as the F block, F as in foxtrot. It's not really what it stands for, but just so you know that this is the F block. Now, I'll show you exactly how I write the electron configuration for tin. I start at the beginning of the periodic table, and I start counting electrons, keeping in mind the maximum number of electrons that are allowed in every orbital. In the s orbital, there are 2 electrons allowed, so this is 1, that's the 1, 1s1. The next element is 1s2, right? So the electron configuration for tin starts with 1s2. After that, it is 2s1, 2s2, so it goes to 2s2. I'm going to start writing these down. So tin is 1s1, 2s2, and then it goes 2p. This is the p block, so that 1, 2, 3, 4, 5, 6, 2p6. That's 2p6. Next I have 3s2. So that's 3s2. And then there's no D for the third row. Can you hear me? Sorry. There's no D for the third row, you see. And this is 3P. 1, 2, 3, 4, 5, 6. So 3P6. 3P6. After that, I got 4S2. 4S1, 4S2. So 4S2. 4S2. And then when you name this D block, you have to name this as a 3D. That is for technical reasons. These D electrons are part of the third shell of electrons. How are they part of the third shell? It is not because they are closer to the nucleus than the 4s electrons, although the d electrons can be closer to the nucleus. This is not why we call this 3D. We call this 3D because the existence of this orbital was predicted using math, and that math predicts that this orbital needs to be part of the number 3 shell of electrons. Right? This 3s2, this 3p6, this 3d10, these 10 atoms right here, they represent positions in the periodic table where there are electrons who exist in a mathematically determined group, and that group is what we know as the third shell. Right? So this is for technical mathematical reasons why we call this the 3D rather than the 4D. All right? It's just important to remember. So this is 4s2. This is 3D1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 3D10. And then this is the P. Oops. How did that happen? Sorry about that. Okay, now this is the P block. But we're going back to the number 4. this 3D is in the fourth row, and it's the only thing that's in the fourth row that doesn't have a 4 by it. So this is 4s2, this is 3d10, this is 3p6. I'm sorry, 4. This is 4p6. This is 4s2, 3d10. This is 4p6. Fourth row, 4p. Okay? So 3d10, 4p6. All right. Now over here, we've got 5s2, 4d10, and then 5p, right? So it's 5s2, 4d10, and then 5p, how many? Well, we're looking for 10, so it's 1, 2, 5p2. Okay? That is the complete electron configuration for tin. Since we're on this subject, let me show you the noble gas configuration. The noble gas configuration is just a shorthand. You just say tin has all the electrons that the previous noble gas, which is krypton, has. Tin has all the electrons that krypton has, plus these other ones, right? So you would go tin is the same as krypton in square brackets, followed by whatever's left, which is this stuff. 5s2, 4d10, 5p2. So here's krypton, and then you put an additional 5s2, 4d10, and 5p2, 1, 2. And there you have tin. That's the electron configuration for tin in the noble gas shorthand notation. Of course, if your if the atom that you get on the final exam is something like lead, and there's an additional complication, so let me just perform that for you, the ground state electron configuration for lead. It goes 1s2, right, so it has everything that tin has, plus some other stuff, so I'll start with tin. So it goes, so lead goes 1s2, it's all this stuff, 1s2, 2s2, 2p6, 3s2, oops, this is an s, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p, in this case it's going to be 6, because lead is down here, so I go to 5p6, and then after the fifth row, there's the sixth row, so 6s2, so I go 6s2, and then I go here. Now you see, this is where the periodic table skips down here. This is the F block. Just in the same way as with the D block, I had to subtract a row number, so these guys were not 4 Ds, but they were 3 Ds. I had to subtract a row number. These are 3 Ds, these are 4 Ds, these are 5 Ds, these are 6 Ds. In that same way, when I use an F block electron, I have to skip 2. So these are not, so this was 6s, right? These are not 6f. These are 4f, right? So these are 6s and these are 4f. So it goes 6s2, 4f. Now, if I count these, there are 14 of them. So 4f14. And then after I get to the 14th one here, next atom is hafnium. And this is in the D. This is in the D orbital. So this is not 6D, but remember, I have to subtract 1, so this is 5D. It's going to be 5D10. I know what you're thinking. You're thinking, hey, but there's only 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, on this periodic table, they chose to include lanthanum and actinium down here. Many periodic tables choose to include them up here. So actually, if you count these, there are not 14, there are 15. You can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Only 14 of these are filling new electrons into the f orbital. One of these, I think it's these two, are filling new electrons in the d orbital. So it would go like this, 6s2, and then starting from cerium, 4f14, and then jumping back over here with this spot being lanthanum, this one, it would be 5d10. Okay, and then this one is 6p with letters right here, so it's 6p1, 6p2, so it's 6p2. 5d10, 6p2. So that is how to do the electron configuration. That was number 7. The dog is sleeping on my lap, so I'm going to remove the dog because it's getting very warm. Put the dog in the laundry basket because that's where she likes to be sometimes. Okay, let's go for number 8. Get you a clean board here. It's best if I make a new board each time because I found that if I write over the same board with another board, after I do that a few times, the program, this Paint program, starts to slow down and become hard to use because of its low speed. All right, what is the enthalpy of reaction for this chemical equation? So here are some heats of formation. This is one of these heats of formation problems where you will do the products minus the reactants. So the products, so yeah, say delta H of the reaction with a little O here. That's what is meant by this nonsense. Equals the sum of the products minus the sum of the reactants. You don't have to memorize the formula like that. You just have to remember that it's all the products minus all the reactants. There are 2 liquid waters, and liquid water has this heat of formation. So there are 2 negative 285.8. These are all in kilojoules per mole, so I'm not concerned about the units. Plus, there are 2 sulfur dioxides, and those are negative 296.1. Negative 296.1. And that's going to be minus all the reactants. Now, the reactants are 3 oxygens. Now, remember, a pure element in its standard form at room temperature, gaseous, diatomic, is going to have the heat of formation of 0. So I don't care about the oxygen. I just care about this. 2 hydrogen sulfide gases. Hydrogen sulfide gas has this heat of formation, and I want 2 of them multiplied by 2. So let me get the answer here so you can check yours against mine. Nice little Apple calculator. So 2 times parenthesis 285.8 negative minus 296.1 parenthesis plus 2 times 20.1. Okay, so I think I get negative 1,123.6. That is the correct number of significant figures because everything is in the tenths place, and this is an addition and subtraction problem. So this is negative 1123.6. The units were kilojoules per mole. This is not kilojoules per mole of hydrogen sulfide gas. It's not kilojoules per mole of oxygen gas. It's kilojoules per mole of this entire reaction. Okay, number 9. I have a little calorimetry problem here. This is going to be one of those problems where you use Q equals MCAT, you know, Q equals MC delta T, or Q equals the mass times the specific heat capacity times the change in temperature. It's one of those guys. So I know that because it says how much heat and it gives me a temperature change. So Q equals MC delta T, where the mass is 10.22 grams. The specific heat capacity of this stuff is 0.900 joules per gram per degree Celsius. So I know I'm going to need Celsius at some point. So the delta T went from 20 to 60, that means it started at 60 and then went to 20. So I get a delta T of 40, a positive 40. This means it got heated up. Is that correct? Yes, it is getting heated up in this problem. So Q equals this 10.22 grams. Perhaps I should do this in a place with some more space. So Q equals 10.22 grams times the C, 0.900 joules per gram per degree Celsius, times the delta T, which is 40.0 degrees Celsius. The degrees Celsius cancel. The grams also cancel. Joules are left. That's good. That means my work is probably correct. 10.22 times 0.9 times 40 is 367.92, but this is a multiplication problem. I only have 3 significant figures, so it's 368. The units are right here, joules. That's how much heat is required to heat up whatever they wanted, using whatever details they wanted. Okay? Now number 10. In a chemical reaction, blah, 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 another enthalpy problem. Okay, this problem requires you to write a chemical equation yourself and to balance it yourself. Looks like I have forgotten to include some important information here, though. You need to know that hydrogen gas is H2, and nitrogen gas is N2, and ammonia is NH3. I'll try to remember to edit the practice exam so I put to add those important pieces of data for you. All right, so we've got nitrogen gas and hydrogen gas, and somehow they combine to form, so this arrow means to form, ammonia gas. So these are all gases. I have to balance this now. Okay, it's balanced. Now I'm going to figure out how much energy gets released if I make 1945 grams of ammonia. So 1945 grams of NH3. Obviously I'm going to have to use the chemical equation, because chemical equation tells us how much of these chemicals we need and how much energy we're going to get from them. Okay, so since I'm going to use a chemical equation, I cannot use grams, I must convert to moles, so let me do that. There are about 17.01 grams of ammonia in 1 mole of ammonia. You can get that by adding stuff up on the periodic table. That's how I expect you to get it. Here, let me show you, just in case you forgot, because it has been a little while. Nitrogen is over here. It's 14.007 grams per mole. And hydrogen is over here, 1.008 grams per mole. So you will 13.008 plus, now there it's NH3, so there are 3 atoms of nitrogen, atoms of hydrogen. So actually I get 20. Is that right? I don't think that's right. 3 times 1.008 equals, and that plus 14.00, was it 7? Yeah, 17.031. Where are you? Yeah, 17.031. So this was actually not right. This should be 0.03. 1. Okay, so grams of ammonia cancel. I found the molar mass, and there it is. Now I have moles of ammonia, but I don't want moles of ammonia. I want kilojoules. I want how many kilojoules I'm going to get. So for every 2 moles of ammonia, strategically place your moles of ammonia to cancel out moles of ammonia. For every 2 moles of ammonia, I get this, this much energy. Because this mole refers to the whole reaction. In 1 mole of this reaction, I get 2 moles of NH3. and for every 2 moles of NH3, I get this much energy. Mr. Calculator is here to help us. Everything on the bottom is divided, everything on top is multiplied. Count significant figures, it looks like I only have 2 right there. So this is 5,300. I only have 2 significant figures, so these are the only figures that are significant. So it's negative 5,300 kilojoules. Kilojoules are the only units left standing here. Let me verify that this is really only 2 significant figures. It seems kind of hard to believe, given that everything else was 4 significant figures. Let's see. Yes, that's right. 2 significant figures, so this is the correct answer, folks. If you put 5,250, that would be wrong. If you put what your calculator said, this number, that would also be wrong, okay? Because of the significant figures issue. A nice, clean, fresh piece of paper, or virtual paper for you. Get rid of this one. Okay. Oops, sorry, that's somebody's chat. Don't want to show you that. Okay. So, okay, number 11. How many of these have I got here? Man, 30? Okay, I'm going to have to break this up into several videos. All right, so number 11. I got a wheel. Okay, so obviously this is volume and temperature. So it's a volume and temperature problem. This is a Charles law problem. Charles law says that the volume that you have at first divided by the temperature that you have at that time is going to be equal to the volume that you have after some change divided by the temperature that you have after that change. So what are we asking for? The new volume. So that means I'm going to want to solve for V2. To do that, I multiply T2 on both sides. These T2s cancel. So I get the fact that V2, write this backwards, equals T2V1, saying one thing and writing another. T2V1 over T1. There it is, T2V1 over T1. There. So these are these are the spoils of this little war over here. Okay, now what was T2? Let's see. After driving a long time, you warm up the air. The new temperature is 73.2 degrees Celsius. Folks, when you use gas laws like this one, you must never use the Celsius temperature. The Celsius temperature includes 0. So what happens if one of these temperatures is 0 Celsius? Then you would have a mathematical impossibility. So we never use Celsius for gas laws. We use always Kelvin. Kelvin does not have a 0 on this universe as far as we know. So V2 equals the Kelvin temperature for T2, which is 273.15 plus that. So 273.15. What you need to memorize, folks, is 273. You do not need to memorize the 0.15 if you don't want to, but you can if you like. Plus 73.2. So the answer here is 346.35. Of course, this is not significant, so it's 346.4. So T2 is 346.4 Kelvin. And the V1, the V1 is this here, 9.7 liters. The volume of the air in the tire is that, 9.7 liters. And the T1, you started out at 25 degrees Celsius, which is 298 K. Actually, it's 298.0 Kelvin, isn't it? Figure out the new volume here. 346.4 times 9.7 divided by 298. And that's in 2 significant figures just like that. That's 11. 11 liters is the new volume of your tire. Does this really happen? You bet it does. This happens all the time. Have you ever seen a tire blow out on the freeway? The air inside the tire was trying to occupy a greater volume than the tire was able to accommodate. So it blows up. You could also interpret a tire blowout on the freeway in terms of pressure instead of volume. As the temperature rises because the truck is rolling, as the temperature inside the tire rises, the pressure also rises until the thing blows up and you have a little freeway trash created there. I think I'm going to stop the video here and continue the rest with separate videos. Thank you.